Okay, hello everybody. My name is Styliani Tsilia. I am a second-year PhD student in the Instituto de Astrofísica de Canarias, supervised by Eduardo Martín, Hervé Bouy, and Marusa Zerial, who just had her talk. And along with a team of collaborators, we are members of the Substellar project team. Today I'm going to talk to you about searching for rogue planets around the Horsehead Nebula. But before I do that, if that works, yes. Okay, quick slide with definitions so that we're all on the same page, because we told you we are members of the team called Substellar. So we are looking for substellar mass objects, and we want to study these objects using data from Euclid. When we talk about substellar objects, we're using the general definition that these objects cannot sustain hydrogen burning in their cores. And these include both brown dwarfs, who lie between the 13 and 75 Jupiter mass range, but also free-floating planets, which are objects with masses lower than 13 Jupiter masses, which is also where we find the deuterium burning limit. Another term that I'm going to be using is that of the ultracool dwarf, or UCD. Ultracool dwarfs are even a more umbrella term, which include both substellar mass objects, but also lowest mass stars. And here we're talking, all the objects that we're looking at are all objects later than type M6. Now, I promised you Horsehead. And why should we care about Horsehead? Why is it interesting? The Horsehead Nebula is a relatively nearby region to us, more or less at 400 parsecs. It has a lot of young objects. It's a region of active star formation, which is always interesting to study. And it also exhibits a very complex structure and a very nice morphology that to me is also very interesting to see if it could potentially affect object formation processes. Also, it's a very well-studied region, which means that there is already a nice groundwork upon which we can build on, and many papers and much literature that we can study. And another reason that we're also interested about the Horsehead is that, as you just saw from Marusa's talks, it's one of the fields that Euclid has already observed. And the first paper from our team, based on the early release observation data, was about this region. This paper's goal was mostly to showcase the potential of Euclid for us to be able to study these substellar objects. And you already saw that image from Marusa. For the purpose of the paper, we divided this field into different regions, one high-reddening one and one low-reddening one. So the high-reddening region is what actually includes the Horsehead Nebula, the embedded cluster NGC2023, this H2 region, IC434, and this is what I'm trying to study right now. The paper itself was based on the low-reddening region, which is to your right, and which is actually the Sigma Orionis cluster. Now, some results from the paper. Marusa just showed you color-color diagrams. I'm going to show you here a color magnitude diagram, which I really like, because we could draw in our data the 3 million year isochron, this is ATMO model, and we could see our UCD objects and our UCD candidates popping along this sequence. And 5 of those actually lie below the 13 Jupiter mass limit if the model is to be trusted. So this could also be nice UCD candidates that are also could be of planetary mass. Another result from the paper is that we constructed the substellar IMF for Sigma Orionis, which is consistent with a broken power law that you can see here, the brown dwarf regime, and then the planetary mass regime over here in blue, along with some complementary data from Gaia, which is for the low mass stars, is what you see in red. But right now, I'm not looking in the low-reddening part, I'm looking in the high-reddening part. And of course, the problem with this region is the high-reddening. Indeed, high-reddening, variable reddening as well. Unfortunately, the dust maps that we have right now are not, I do not have good enough resolution, which means it's not as easy as going to the CMD and nicely and reliably de-reddening each and every object to get a nice and reliable CMD with all the objects de-reddened. What we can do is to use some lower limits to try and constrain our ultracool dwarf candidates in this field. And that's what I have been trying to do. So in order to do that, I'm using a denebulized catalog. I computed a renewed filtering criteria for this catalog, but based on the process that is described in the early observation paper. I combined the data from Euclid with some ancillary data from Spitzer. And I'm also using the Atmo 3 million year isochron as well. Why 3 million years? In this region, the age range is a bit broader, but I'm using 3 million years as a good average and also as a good place to start. And to show you what this looks like in practice, this is again from the paper to compare. You see how the objects that we care about lie very close to this isochron. What I had was more like this. So no nice sequence, no nice objects lying around the isochron. Everything is reddened. And as I just told you, I cannot just go and de-redden each and every object. So what's the next best thing that can be done? One thing is to say that, okay, the objects that we're looking for, they are red, they are faint. We are in a high-reddening region, so they can only get redder. So my first cut to try and approach UCD candidates in the field would be to go and select everything to the right of the isochron here in this CMD, and basically selecting all of the red objects. And of course, I didn't stay just in one CMD. I did this with all of the CMDs that I could construct with Euclid. And then, as I just mentioned, I combined that with data from Spitzer, built those CMDs as well, which leads me to my selection criteria. The selection criteria for my first sample of the UCD candidates would be choosing the objects that lie consistently to the right of all of these isochrons, which means that if an object exists in any of these CMDs, it is selected if it lies to the right of the isochron in all of the CMDs where it exists. And I'm also including some objects that I realized I was throwing out because due to a filtering process, because they were not detected in all bands. So this process led me to a first sample of candidates of 194 objects, which also, of course, include some free floating planetary mass object candidates. And this is what they look like in the field. Now, apologies if it's not very nicely visible here on the screen, so I'm going to also use my cursor. What you see here, this is the field from Euclid, and this is the low-reddening region to the right, high-reddening region to the left. And all the green triangles, which I will point out some of them, all of these objects, all of these points, are the objects from the ERO paper, and these are the objects that were lying along this isochron. And as you can see, so the UCDs, known objects, and also the candidates, and as you can see, they are more or less randomly distributed in this field. Now, on the left, the points here, all this blue, they are my first list of 194 objects that I just mentioned. And when I first saw that, I was a bit perplexed because, as you can see, contrary to the low-reddening region, the candidates that I find in the high-reddening region, they seem to be spatially clustered or to have some sort of spatial distribution. So there is something like a halo around this embedded cluster here. Some of them go to the Horsehead. There are some of them in some small gatherings down here. So I was a bit perplexed about this, because if this was a reddening selection, if this image arose because of the reddening, then I would expect the reddening maps to sort of follow this gradient of candidates, and this doesn't happen Like there is no clear correlation between where these candidates are and how the reddening map looks like. Then I started thinking, okay, could it be the morphology of the horsehead? Maybe the unique morphology of the area has some influence on the formation processes. Maybe the H2 region is expanding, gas is being compressed, and this also affects star formation, which is something that has been proposed in the literature before, I think in the paper by Mokirdzea back in 2009. But then again, on the other hand, these are a bit too many objects. I wouldn't expect all of them to be UCDs. On the other hand, I would expect most of the foreground contaminants to be thrown out completely due to the high reddening. I would expect them to be even more reddened and extinct. Of course, contamination cannot be fully eliminated. And doing a quick crossmatch with SIMBAD, around 5 of the 194 objects are known objects. They are in SIMBAD, and they are listed as young objects, which is consistent with what I would expect. But that indeed is telling me that, okay, these are a lot of new objects indeed. And of course, I can sit here and speculate all I want about this region, but the next step would be to look into the spectroscopy to be able to understand at what I'm looking at exactly. Just like Ray said previously, it's very important to look at the spectroscopy. So this is a process, it's a troublesome process. It's done in collaboration with Carlos Dominguez-Tagle, which is the member of our team who is our in-house spectra expert. And I'm very happy to show you that one of those candidates, which was in my list, candidate number 145, I think, I got the spectrum back from Carlos, and you can see like this, which is the water drop that we would expect to see in a UCD, and the two-peak structure. And I was very happy when I got the email from Carlos back, sending me this and telling me, okay, we have one confirmed UCD object thanks to spectra. This spectrum is still a work in progress because it's not calibrated yet. Like this is not wavelength, this is just the pixels. And still there is some instrumental and some extinction corrections that need to be accounted for here. But still the water drop, it's super clear. And I was really, really happy to see that. Now the next question would be, okay, if we say we find one UCD so far, could this be potentially a planetary mass object? If I take you back to the color magnitude diagram, this object, this UCD, this candidate, is down here. And of course, all of this is reddened. So in order to de-redden it, we would have to bring it upwards in this diagram. And then the question is, okay, if I try to de-redden it, will it still appear to be, according to the model, lower than 13 Jupiter masses or higher? What can I do to de-redden it? Can I possibly use some reddening vector? This is the reddening vector that was in the ERO paper. And okay, if I take this specific vector and I try to de-redden it, then it will still lie pretty low in this diagram. But this is not enough. This reddening vector was created based on the fact that I think 70% of the sources in the whole field would have a maximum up to this extinction. But of course, as I told you, high reddening, variable extinction, it's not that easy. I tried using 2 different reddening maps. It's what Marusha alluded to. And you can see that they do not agree. So this is the result trying to de-redden with Edenhofer and Bagestar. Very different things. If anyone here has any good ideas about how to treat like a high reddening, like variable reddening area, I would be very happy to hear your thoughts. Because of course we're not stopping there, the search continues, the spectroscopy is an ongoing process, and now that we also got the first object, I am optimistic about what else Carlos will be able to share in the following days. Now, just to summarize what I'm seeing here, new UCD candidates, also including free-floating planetary mass object candidates in the high-reddening region of this field from Euclid. These candidates seem to have some sort of spatial clustering, unlike the candidates in the low-reddening region. The spectroscopy is ongoing, and we currently have one UCD object confirmed. A reminder about our substellar conference next year. We'll be very happy to see you there. And with that, I'm going to thank you, and I'll be happy to take any questions.
Questions or comments?
So I'm not an observer, so I might be completely confused. But yeah, it's very interesting that you have these two, fields. One is highly extincted, the other one is not. It'd be really interesting to also look at these, stellar populations differences in these two regions, because when I think about star formation, there's a collapse, right? And the time scales can be relatively long, a million years or so as well. So, and if you have ejection of planets from these environments, and depending on their velocity, some of them can actually travel out of these, and so then you could predict a population difference in the extincted and non-extincted regions, just because if free-floating planets are traveling fast, then they could get out of the extincted regions. So something like that would be really interesting, I think.
It would be interesting to keep in mind. Thank you. Yeah, because so far I was taking a deep dive in literature, but for the high-reddening region, so there have been many young objects observed before there. But nothing like the spatial clustering that I showed. But of course, I'm not still sure about that and exactly what I'm seeing. But yeah, I didn't try to compare populations. So thank you for this suggestion.
Also a question from Matthew.
Very nice talk. You said you picked candidates based on everything redward of the isochron. How many of the sources did you only have like 2 photometric bands for versus all of the photometric bands? And how many sources do you think you have reasonable spectra for?
Okay, I'm going to start with the first one. So most of them that ended up in the sample, because I checked after I had the sample, they actually had the photometry in all of the bands or in 3 out of 4 of the bands. So what I mentioned that I'm including just some extra objects just to be a little bit looser in my selection criteria and not throw out potentially good candidates if something happened in one of the bands and one of the photometries is missing. But in general, most of the photometry was there. So I was not selecting objects with only one band, let's say. So I'm pretty confident about that. And then the spectra part. So the spectra, it's a shame that I don't have a photo here to show you, but because it's slitless and it's quite messy and noisy, and Carlos is really working very hard on that, but it takes a lot of time. So what I did, I started with a high purity, let's say, sample of candidates to be extracted with very, out of the 194 objects, with some very strong criteria about the ellipticity, the factor of some flags from the Euclid data, like the cluster, and out of the 20, let's say, high purity sample, then for Carlos to get a good spectra, he needs at least 2 ditherings of the spectrograph to be like a good data object. So at some point, I think we had 7 or 8 that were not UCDs that Carlos was able to get. Then this one that appears to be UCD. Another one that we are not sure yet, because there is something like a water drop, but we need to, like after calibration, we will go back to it. And now I'm trying to revise my method once again, because I'm not sure if I'm throwing out, again, good candidates just by setting these very strict criteria. So right now, I would say how many spectra in total? About 10. Yeah, and again, we're working actively with Carlos to see how we can optimize this process.
Thank you.
Okay, let's thank Stella once more.